So continuing our discussion about other functions, I'm going to look at a more specific type of functions called reciprocal function. It might be called functions when the power of x is negative, so it can be described in a different way, but formally they're called reciprocal functions. So this is when the power of x is negative, or x is in the denominator. And I'm looking at the simple case where you only have x in the denominator. I'm not looking of when x is in the numerator. Those are different types of functions. So these functions, I'm going to be dealing with the simple ones as well. So not much in the denominator except for x. So something like if I say y equals to x to the power of a negative 1. Well, we've discussed this before, that any x to the power of a negative 1 is the same as reciprocating it. So it's the same as saying x is in the denominator and now the power is positive. So the same thing would apply if you had y equals to x to the power of negative 2, then this just means that x is in the denominator and it's squared. So it's just easier notation if I bring it to the numerator, but to indicate that it was actually a fraction, I'd have to put the negative sign. The rule behind this, using laws of indices, can prove why the negative exists. So y equals x to the power of negative 1, which is the same as 1 over x. And if I graph this on a calculator, so if I graph it on a calculator, it's going to give you quite a distinctive function, and you're going to see why that is. So until the JDC loads up. So you're going to get if I have 1 over x, and please watch the previous video to see what you should do if you need to fix your window or anything. For this case, it's fine. We could do it from 10 to 10. And I could change the scale of the x-axis, so y-axis, so I want the scale to be a 5. So as you can see, it goes down here and then it jumps up there. And if I keep on zooming in, and where it seems like it's catching the y-axis, you'll notice that it actually never touches the y-axis, and you can keep on zooming in. If we go to second table, you'll notice the values getting so as x value is increasing, your y value is getting very tiny, and as your x value gets, well, it would be preferable if we had decimal points here, so 0.1, 0.2, so in between 0 and 1, the y value is actually really big, and it goes up to infinity, and you'd notice that 0 is, when x is 0, you have an error. Now, all of these properties are quite distinctive or special with reciprocal functions. So this function is actually defined as, well, I have a graph y equals x to the power of negative 1, but I have to tell you that x can never be 1. So this is the formal definition of the function. Now, x can't be 1 because if x can be 0, because if 0 is in the denominator, you'd get an error. And this is where we got this graph. So you see, as the values of x would get very close to 0, your y values are getting really, really big. And similarly here, as your x value is getting very close to 0, your y values, so notice this point, at this value, your y value is here. So you have this. And then if I get even closer, closer to 0, my y value will be even bigger. So they go up to infinity. Either y goes up to either positive infinity or negative infinity. But there's no y value for x equals to 0. So if my input is x0, there's no output. And this line, so you can conclude that this line, this vertical line, has no solution. So this is called an asymptote. And we've discussed asymptotes and exponential functions as the line that the graph gets very close to but never touches. But this is a vertical asymptote now. And vertical asymptotes are much easier to calculate because you just look at the table in your GDC and look at where you'll get an error. And that will be your asymptote. And asymptotes are the vertical asymptotes are in the form x equals to something. So if I tell you what's the vertical asymptote of this graph, you're going to tell me it's x equals to 0 because I'm not allowed to put 0. Now, a bit extra, and these are not included in your book. Let's say you have, sorry, this is included in your book. If I have y equals x to the power of -2, so we said that's 1 over x squared. And what value, if I put in here, would not be defined, would give me an error. So obviously it's 0. So this function is not defined at x equals 0, which also means that the vertical asymptote is x equals to 0. So if I graph this function, if I quickly graph this function, and I know that the line here at x equals to 0 will not be touched and it will not be crossed. And the graph of this function is actually something like this. So you don't actually get negative y values. So there's no value for y when x equals to 0, so x equals to 0 is an asymptote. And you notice that the y values tend to very large positive numbers when x is getting very close to 0 from both sides. So this is just a property of asymptotes. So you either can look at vertical asymptotes as when the function is undefined, or you can look at it as the value. I'll just describe it. So it's vertical asymptotes occur when the value of y tends to infinity as x tends to 0. So as x is getting very close to 0, so x is getting close to 0, y is going up to infinity. So this is when asymptotes occur, and it's just a technical description for it. So if we go by our basic definition of asymptotes, if I give you y equals to 1 over x plus 2, and let's think what value, well, in general, the only value that would make an error here, the only time we'd have an error here is when the denominator is equal to 0. So that's why this was just 0 and this was 0. So if I put 0 in here as my input, so if I put 0, I'll get 1 over 2. So that's fine. It works. I have an output. What value, if I put in there, would actually give me a 0 in the denominator and therefore give me an error? And if you notice, that would be -2. So if I input -2 for the x, so let me do it in different colors, so -2, and then add 2, then I'm going to get 0. And that's going to be undefined. And so my vertical asymptote is actually x equals to -2. So if you're going to graph this, you'll notice at the graph exactly at -2, you're going to get that vertical asymptote. In another video, I'm going to talk about more complex functions, but in general, you can follow the same steps as I did in the previous video for reciprocal functions, where you just need to understand these functions, and as long as you can graph them, then you can answer questions. For example, find the temperature at x equals to this, or find the maximum amount, or find the minimum amount. So these are much clearer with the graphs that you're going to do, and it's essential that you just understand the vertical asymptotes, horizontal asymptotes, and the domain and range. So quickly about horizontal asymptotes. So as you can notice, the horizontal asymptote here is y equals to 0. And that's because as x gets very big, y gets very close to the x-axis but never touches it, and similarly here. So these can be observed from the function. There is a specific method, but it's beyond the syllabus.